I'm Nurul Hazrina binti Nordin from UMPSA STEM Lab, the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah, the instructor for this course.
Welcome to Chapter 4 of our micro-credential course on Raspberry Pi. In this chapter, we will explore how sensors communicate with microcontrollers using different communication protocols. By the end of this module, you will be able to interface an accelerometer with the Raspberry Pi Pico, read sensor data, and process it in Python. Communication protocols are the foundation of how microcontrollers interact with sensors and external devices. In embedded systems, three widely used protocols are SPI, I2C, and UART. Each of these has different speed, wiring complexity, and data transfer methods, making them suitable for specific applications. Understanding these protocols is key to working with various electronic components. Throughout this module, we'll connect an accelerometer to a Raspberry Pi and read the accelerometer data, working with I2C protocol for communication, and processing sensor data in Python. I2C, or Inter-Integrated Circuit, is a two-wire communication protocol designed for simplicity and scalability. It consists of a serial data line, labeled as SDA, and a serial clock line, labeled as SCL. The master device sends commands, and multiple slave devices can respond based on their unique addresses. This protocol is widely used in sensors like temperature modules, accelerometer, and displays. SPI stands for Serial Peripheral Interface. SPI is a high-speed, full duplex communication protocol. Unlike I2C, the SPI uses 4 lines: the MOSI, which stands for Master Out Slave In, the MISO, which stands for Master In Slave Out, SCLK for Clock, and CS for Chip Select. This protocol is best suited for applications requiring fast and continuous data exchange, such as display and memory devices. And finally, the UART, the Universal Asynchronous Receiver Transmitter. UART enables serial communication between devices. UART is a widely used protocol that allows two devices to exchange data asynchronously, meaning without a shared clock signal. Instead, it relies on two main functions: TX or transmit and RX or receive. Let's begin with the TX function. The transmit pin sends data out from the device in a serial format, 1 bit at a time. Before transmissions, parallel data such as sensor readings or microcontroller outputs is converted into a streams of bits. The data is sent following a standard structure: a start bit, data bits, and optional parity bit. A start bit, data bits, an optional parity bit for error checking, and a stop bit. Now, let's have a look on the RX function. The receive pin listens for incoming data. When it detects a start bit, it begins capturing the data bits and reconstruct them into meaningful information. The received data is then converted back into parallel data for processing. One important rule in UART communication is that the TX of one device must always be connected with the RX of another. This ensures proper data transmission. Additionally, both devices must operate at the same baud rate, for example 9600 bit per second, to avoid data loss or corruption. UART is commonly used in microcontroller sensors, GPS module, and Bluetooth devices, making it a fundamental communication method in embedded system and physical computing. In summary, TX sends data, RX receives data, and proper wiring ensures successful communication. Each communication protocol has its advantages. I2C is great for multiple sensor connections with minimal wiring. SPI is ideal for fast data transfer but requires more connections. UART is a simple and effective for device-to-device communication, but is limited to one-to-one connections. Choosing the right protocol depends on your project's requirement. Accelerometer are sensors that measure motion, tilt, and vibration. They detect acceleration along three axes, X, Y, and Z. The X-axis represents side-to-side movement. The Y-axis represents forward and backward motion. And the Z-axis represents the vertical displacement. They are commonly used in robotics, gaming control, and fitness wearables. Many accelerometers, such as this MPU6050 or ADXL345, communicate using I2C, making them easy to interface with Raspberry Pi Pico. Additionally, accelerometers are often used in combination with gyroscope to measure angular motion, enabling the calculation of yaw, pitch, and roll. Yaw refers to rotation around the Z-axis, left or right turning motion. Pitch refers to rotation around Y-axis, tilting up or down. And roll refers to the rotation around X-axis, tilting sideways. This is an example on how to connect your accelerometer with Raspberry Pi Pico. Here is an example of Python script to read data from MPU6050. The Python script initializes I2C connections and sends real-time acceleration data from MPU6050 sensor. The sensor provides X, Y, and Z axis readings, which can be used to detect motions and orientation changes. Let's move on to Activity 5 using accelerometer with UMPSA STEM Cube.